Exponent rules. Exponent rules. Exponent rules give us a quick way to multiply and divide variable expressions. For some of the rules, we will work through and discover them. For some, we'll just look at examples. Let's look at this first example, x cubed times x squared, and try to figure out the rule for multiplying variables. If we write out what x cubed means, it is x times x times x. And we have multiplication in between. If we write out what x squared means, it is x times x. Now, if we put this back into exponential notation, x is our base, and we have 5 copies, so 5 will be our exponent. Our situation is that we had like bases, we had both x, and it is a multiplication problem. So like bases multiply, we're going to keep the base and add the exponents. The 3 plus 2 gives 5. So keep the base, add the exponents. Let's look at another example. X cubed times x. If we write out what it means, x cubed is x times x times x, and then we have another x all multiplied. So if we go to exponential form here, we have one base, which is x, so we keep the base, and we have 4 copies of the x, so our exponent is a 4. So when you're adding the exponents, if you don't see an exponent, remember to add a 1. So we have to do 3 plus 1 to get 4. Let's look at another example. 2 to the 3rd times 2 to the 4th. A long time ago, we learned to do this problem with order of operations. And so we would do the exponents first, and then we would do a multiplication. But it is set up so that we could use exponent rules because we have the right situation. We have like bases, the base is 2 for both, and it is a multiplication problem. So our rule says keep the base and add the exponents. So 3 plus 4 is 7. Let's look at one more example. This problem looks quite a bit longer. What we want to notice is that it is multiplication between the parentheses, and it is all multiplication on the inside of the parentheses. So we can use the associative law of multiplication to rearrange it. If you only have multiplication, your order doesn't matter. So I'm going to pull my numbers. So -5 times 3, and then my x's, x cubed times x to the 4th, and then my y's, y squared times y. So I'm just putting the things that are alike together. And now I'll go across. So for my numbers, I'm going to do plain old multiplication. You only have one negative, that's odd, so it's -15. For my x's, you have like bases multiplied. Keep the base, add the exponents. For the y's, same situation, like bases multiplied. Keep the base, add the exponents. You have to remember to add the 1 for this y. So 2 plus 1 is 3. Our next exponent rule that we'll look at is called the power rule. Let's look at this example and try to figure out the exponent rule for this situation. So we have a base to a power, and the entire thing is raised to a power. If we write it out for the outside exponent, it says 2 copies of everything inside. So we would have x to the 4th times x to the fourth. If we use our rule we learned earlier, which is like bases multiplied, keep the base and add, we would figure out that we have x to the 8th. Or if we didn't know that rule, we could write it all the way out. X to the 4th is 4 x's. And x to the 4th is 4 more x's. And if you go back to exponential form, you have 8 x's, which gives you the x to the 8th. So if we're looking just at our original problem and trying to get the rule, with our exponents, when we have one power raised up to another power, they're going to multiply. So our rule here with one power to a power is keep the base and multiply on the exponents. So to write out our rule, if we have a power to a power, so we only had one base in this problem, to a power, the entire thing is to a power. So we'll call it a power to a power. We keep the base, so we kept the x, and we multiply on the exponents. Let's look at another example. So we have x squared to the 5th power. So it is a power to a power. We only have one base to a power. It's raised to another power. So this is the situation of a power to a power. We're going to keep the base and multiply the exponents. So 2 times 5 gives us 10. Exponent rules. The power of a product rule. Our situation in this example is that we have a product to a power. It is important that it's multiplication inside. And so we're going to apply that outside exponent to each piece. If we wrote it out, it would be 3 copies of the whole thing. Instead, we'll just apply the 3, take it down to each factor of the product, and that will do the same thing as writing it out 3 times. So 3 of each of those. So we'll have 2 to the 3rd, x to the 4th to the 3rd, and y squared to the 3rd. And now we'll simplify each of these pieces. 2 to the 3rd will actually be 2 times 2 times 2, which gives us an 8. The next one, x to the 4th to the 3rd, actually kicks back into our last rule. We have a power to a power. Remember, keep the base and multiply. So that's going to give us x to the 12th. Same thing for the y's. Keep the base and multiply on the exponents. But notice for the 2 to the 3rd, the 2 actually just raised to the 3rd power. It was not an exponent to an exponent. It was just a base to a power. That power to a power is for an exponent to a power. Let's look at another example. Again, we have a product. It's all multiplication inside to a power. So we're going to take the outside exponent down and distribute it to each piece. So we will have -4 to the 2nd power. We will need to use parentheses because the negative is on the inside of the parentheses originally. So we will need to keep it inside parentheses, so it will go to the power. We have x to the 7th to the 2nd power, and y to the 5th to the 2nd power. Remember, the number will actually raise to the power. So it's negative 4 times negative 4 will give you a positive 16 because you have two negatives. For the variable, it is a power to a power. So you're going to keep the base and multiply the exponents. Same thing for the y. Keep the base and multiply on the exponents. Let's look at one more example. This problem is going to have a combination of our three rules we've looked at so far. So when we look at it, we're going to have to simplify each set of parentheses separately and then work with the whole problem. So we'll just concentrate on the first one, a product to a power. The 3 will apply to each piece inside. And so we'll have a negative 2 to the third power, x to the 8th to the third power, and y cubed to the third power. Now let's work those out. Remember, the negative goes to the power, so negative 2 times negative 2 times negative 2 will give you a negative 8 because you have an odd number of negatives. For your variable, a power to a power, keep the base and multiply on the exponents. So 8 times 3 is 24. For the y, also keep the base and multiply on the exponents. 3 times 3 is 9. Now let's look back at our problem. Notice your parentheses are side by side. Remember, that means multiplication. So we're going to have a multiplication in here, and we also had it here. Then we'll go to the second set of parentheses. That is a product to a power. So we're going to take the power down to each piece. So apply the 2. So we will have 5 to the second power, x to the fourth to the second power, and y to the second power. You didn't have to write this one in parentheses. It's really y to the first to the second power, which they would multiply, and it's still going to give you 2. So you can actually just go ahead and put the 2 on the y. Now we'll work these out. 5 squared is 5 times 5 is 25. For the variable, keep the base and multiply. So 4 times 2 gives us 8. And the y is already worked out. Now let's look at the problem we have. Everything is all straight across, so they're all multiplied. For multiplication, remember, you can change the order because of the associative law of multiplication. So I'm going to rearrange it. I'm going to move my numbers and put them together. So negative 8 times 25. Then I'm going to put my x's, x to the 24th times x to the 8th. And my y's, y to the 9th times y squared. For your numbers, we're going to do a regular multiplication. It will be negative because we only have one negative. 8 times 25 will give us 200. For your x's, now we're back to our very first rule. We have like bases side by side. Your rule is keep the base and add on the exponents. So we're going to keep the x, add the exponents, will give us a 32. And for the y's, we will keep the base and add the exponents. Exponent rules. The power of a quotient rule. Our next rule is for a quotient, also known as a fraction of different bases, to a power. We will take the outside exponent and apply it to the numerator and to the denominator, making two small problems instead of one large problem. For our next example, 2/3 to the 4th power. So we will take the 4 with the numerator and with the denominator. This will give us 2 to the 4th over 3 to the 4th, and then we would work those out. 2 to the 4th, it's 4 copies of the 2 is 16. 3 to the 4th, 4 copies of the 3 is 81. This will give us the same answer, but in a shorter form than making 4 copies of the entire fraction. For our third example, 2x to the 5th over y to the 4th, the entire fraction to the 3rd power. We will apply the 3 to the numerator and denominator, making 2 problems instead of 1 large problem. And then we'll apply it to the denominator. On the numerator, you're now back into one of our other exponent rules, which is a product to a power. So you're going to take the 3 to each piece. This will give us 2 to the 3rd times x to the 5th to the 3rd. We can work those out. 2 to the 3rd is 8. X to the 5th to the 3rd. We'll keep the base and multiply. And for our denominator, a power to a power, we can go ahead and work that out. Keep the base and multiply. Exponent rules. The quotient rule, also known as like bases as a fraction. For this problem, we're going to try to figure out the rule when we have like bases as a fraction or a quotient. So we'll write it out. X to the 7th means that we have 7 x's. 1, 2, 3, 4, 5, 6, 7 on the numerator. And x squared means that we have 2 x's on the denominator. When you have products, you're allowed to divide out common factors. So we are able to match up and divide out these 2 x's. Now let's see what we have. Total, we have 5 x's, or x to the 5th in the numerator, nothing in the denominator, but we were really dividing, so the denominator is a 1. You don't have to show a 1 in the denominator. So what could we do just with the 7 and 2 to get the 5? We subtract. So dividing these factors out, we can subtract them off, or subtract the exponents. So for example 2, we have a direct application of the rule. Like bases as a quotient or fraction, we will keep the base and subtract the exponents. 10 minus 2 is 8. Example 3 looks like a much more difficult problem, but it is really just 3 small problems put together. We have numbers, we have x's, and we have y's. For your numbers, you will just reduce like a normal fraction. These have a common factor of 3, so we can divide by 3. 3 into 3 goes 1 time, and 3 into 6 will go 2 times. For your x's, you have a fraction. Keep the base and subtract. You have x squared. For the y's, keep the base and subtract. Don't forget, this one has a 1 if you don't see an exponent. So 5 minus 1 will give us 4y's, or y to the 4th. And then you would want to recognize this also without the 1 in the numerator. It's okay to have it on there, but a simpler form would leave it off, because 1 times x squared y to the 4th would just give you x squared y to the 4th, so you don't have to have the 1. Exponent rules. A zero exponent. Our next rule, x to the 0 equals 1, is really a definition. A definition is made anytime there is something in a gray area. Let's recall what 2 to the 3rd means. It means to take 3 copies of the base. So nice, concrete meaning, and then you could work it out. But if we tried to have a 0 for an exponent, how do we make 0 copies of something? So we have something that's a little gray. Let's see where this might come from. Let's think back to some old problems for a moment and to see maybe why this definition of x to the 0 is equal to 1. First of all, let's think about 3 divided by 3. I think we all would agree that is equal to 1. Anything divided by itself goes 1 time. And how about x to the 5th divided by x to the 5th? This is also going to be 1. We could write it out. But we are dividing, and everything divides out and it goes 1 time. Now, if we tried our previous exponent rule of like bases as a fraction or a quotient, the rule was keep the base and subtract the exponents. And so this is where this new piece is showing up, this x to the 0. So we want that to be defined as the real answer to this problem, which we know is 1. So this is kind of where this definition comes from. This is a situation where it shows up by 5 minus 5 gives us the 0, but we know this is equal to 1. Now, this was just to help you understand. What you have to know is how to apply this definition. We will use our definition to help us simplify these two problems. What you want to notice is what is the 0 really with? In the first situation, the 0 only applies to the x. So this piece of it, the x to the 0, is 1, but you still have it multiplied by 3. So our answer there is 3 times 1 is 3. For our second situation, the 0 is beside the parentheses, so the 0 applies to the entire piece. This one is equal to 1. It doesn't matter what's inside, the entire piece is to the 0 power, so that is a straight application of your definition. Let's look at this example. Simplify negative 5x to the 0. So we want to know, what is the 0 really with? It is only with the x, so that piece of it is equal to 1 by definition, times the negative 5 will give us negative 5. This last example is often used as a type of trick question. It looks really hard. That's very complicated on the inside. But what you want to notice is the 0 is beside the parentheses, so it applies to the entire thing. So by definition, this is equal to 1. You really don't have to do anything. It is something to the 0 power, so it is equal to 1. Exponent rules. We'll summarize our exponent rules. Our first exponent rule was when we have like bases multiplied, and our rule is to keep the base and add the exponents. Our next rule we had was a power raised to a power, and we will keep the base and multiply on the exponents. Our third rule was if we have a product to a power, we take that outside exponent down to each piece of the product to give us a to the m, b to the m. Our fourth rule was a fraction of different bases to a power, or a quotient to a power. And we will take the outside exponent with the numerator and with the denominator to make two small problems instead of one large problem. Our fifth rule was a fraction of like bases, or a quotient of like bases. And we're going to keep the base and subtract on the exponents. Our sixth rule was a definition. X to the 0 power, or anything to the 0 power, is equal to 1. Negative exponents. We have two definitions to help us simplify expressions with negative exponents. X to the negative n is equal to 1 over x to the positive n. So if we have a negative exponent, we can shift it to the denominator and make the exponent positive. And the second one, 1 over x to the negative n, is equal to x to the positive n. So if it's in the denominator with a negative exponent, we can shift it to the numerator and make the exponent positive. Let's look back for a moment and see why we need a definition for something to a negative power. Let's go back to positive exponents for a minute and say we look at 2 to the third. Right. This has a nice clear meaning. It means take 3 copies of the base. And then we can work it out. But what if we try to make a negative number of copies? How do we make negative 3 copies of the 2? We can't. So this is why we need a definition. It doesn't fit with our old definition. Let me show you a little bit of why they make it this particular definition, an example of where it comes from. If we look at a problem, say x to the third over x to the fifth, and we can write those out to see the picture of what this means. It means 3 x's on the numerator and 5 x's on the denominator. And once you have products, you're allowed to divide out common factors. And so I have 2 x's left in the denominator. Remember, if everything divides out of the numerator, then it's a 1. You have to write the 1. So we know this is the right answer to this problem. The picture does not lie. If we try to use our subtract rule for exponents, we would have 3 minus 5 would give us x to the negative 2. So this would be where a negative exponent is showing up. We want it to have the same answer as the problem it comes from. So this is going to equal 1 over x to the positive 2. So to work with it, you can just shift something with a negative exponent to the opposite place. If it doesn't show a denominator, then it's automatically in the numerator. Shift it down, change the exponent to positive. In general, we want to write expressions with positive exponents, with the exception of scientific notation. So if we have an expression with a negative exponent, notice the word negative and exponent. It can be shifted to the opposite position and the exponent changed to positive. You always have two changes. So if something has a negative exponent, it's going to shift. If it's down, it goes up. If it's up, it goes down. And the exponent will change to positive. Let's look at some examples. First, we have simplify x to the negative third power. This one is just a direct application of our definition. So we're going to rewrite it. We're going to shift this x to the negative third to the denominator. The exponent becomes positive. For our next example, we're going to simplify a to the fifth times x to the negative 2 power. You want to make sure that you only move the right pieces. So there is no reason to move the a. It has a positive 5 for an exponent, so it is going to stay. The one that is a problem is the x because it has a negative exponent. So we're going to make a fraction form. The a is staying in the numerator. The x is going to shift down, and the exponent changes from negative to positive. For our next example, simplify x to the negative fifth over y to the third. The x is the piece that's no good. It has a negative exponent. So it's on the numerator. We're going to shift it to the denominator. The y is fine. It has a positive exponent, so we're going to leave it where it is. So the x is going down, gets a positive exponent. The y is staying. And I just kept them in alphabetical order. That's why I put the x first. Remember, when everything goes out of the numerator, you have to show a 1 so that you see it is still in fraction form. For this example, notice the x to the negative 2 is in the denominator. This is the piece that's no good. Your constant is fine. It is down, so we're going to shift it up. The 6 is staying. The x shifts. The exponent becomes positive. When everything shifts out of the denominator, you are not required to write the 1 in the denominator. Our next example, simplify negative 3x to the negative 2 over y to the third. There is only one piece in this problem that is no good, that will need to shift, and that is the x to the negative 2. It has a negative exponent. The negative 3 is fine. It is a constant, not an exponent, so we don't shift it. So we're going to keep the negative 3 and the y to the third where they are. And the x was on the numerator, so it's going to the denominator, and the exponent changes to positive. Next, we will simplify 5 to the negative 2 power. You cannot do any evaluating here. We cannot make negative 2 copies of the 5. So first we have to use the definition and change it over to a positive exponent. So right now it's in the numerator. We're going to rewrite it, shift the 5 to the denominator and make a positive 2. So we have to show a 1 in the numerator. So 1 over 5 to the positive 2, now we can work it out. 5 squared does have a meaning for us, but it is in the denominator. 5 squared gives us 25. So remember, shift this first before you try to evaluate. There are two approaches to this next problem. I'm going to show you both, and you can try and see which you prefer. It doesn't matter. One is as good as the other. One thing we could do is we could use our old rule. We have like bases as a fraction, and our rule was keep the base and subtract the exponents. If you're going to use this rule, you should write it out so that you don't make a sign error. Negative 2 minus for the rule, a negative 5, and then you'll clean up. Minus a negative makes plus. Gives us x to the positive 3, so it stays on the numerator. The other approach to the problem is to shift first. We already have a fraction form, so shifting is not going to make it any more complicated. So we have a negative exponent. This one's on the numerator. It's going down. This one has a negative exponent, so it is going up. So now we have x to the 5th on the numerator and x to the positive 2 on the denominator. You still have like bases as a fraction. You're going to keep the base and subtract the exponents. But it's easier to subtract the positive ones in your head. Go top to bottom when you use the subtract tool. So 5 minus 2 gives us 3. So x to the 3rd. So you can use either one that you like. Basically, when I have two approaches, if I already have a fraction form, I don't care. I'll use either one. If it's not in a fraction form, I tend to save the shifting until last. Here is one more problem that we'll look at with two approaches. It is in a fraction form, so it doesn't really matter which I do first. This is like three little problems all put together. So I have my numbers, I have my x's, and I have my y's. So first I'll just use our old rule, our subtract top to bottom for a fraction. Remember, for numbers, you do plain old reduce, and we only have one negative, so it's going to be negative. It does not matter where you write the negative. And we have a common factor of 2. 2 goes into 2 one time, and 2 goes into 10 5 times. For the x's, we're going to subtract. Remember, subtract top to bottom. So we have 5 minus a negative 2. Minus a negative makes plus, so we get x to the positive 7. When you use the rule, it goes on the numerator. Then we'll do the y's. Y to the negative 4 minus for the rule, a negative 3. Clean up, minus a negative makes plus. You get y to the negative 1, which is going to make it go to the denominator. So you get 1 over y to the positive 1, or 1 over y. So we're okay up here. We don't have to write the 1. We have something else there, the y. And if you have something in the numerator, you want to recognize it without this other 1. You don't need the 1. 1 times x to the 7th is still x to the 7th. So you would want to recognize this as an equivalent answer. The other way to do the same problem is by shifting first on the pieces with the negative exponents. So the y to the negative 4, the x to the negative 2, and the y to the negative 3 are the pieces that I'm going to move around. Keep my fraction form. My constants stay. My positive exponent stays where it is. This x is going up, and it gets a positive exponent. The y's are actually just going to switch places. The 4 is coming down. The 3 is going up. And now we'll work with what we have. We have numbers, we have x's, we have y's. So first of all, for the numbers, we'll reduce. We only have one negative. That's odd, so it's going to be negative. We have a common factor of 2. So divide by 2. 2 into 2 goes one time. 2 into 10 will go 5. For the x's, they're side by side, so keep the base and add. So that's x to the 7th. For the y's, you're going to subtract. 3 minus 4 gives us y to the negative 1, which makes it go to the denominator and get a positive, so it will be 1 over y. We already have something on the numerator, so we just have to put the y in the denominator. And then you will want to recognize it without this 1 because you have something else in the numerator. So this is an equivalent answer. And we did get the same answer as we did before. So if I have a fraction form, it doesn't matter which order I apply the rules. If I don't have a fraction form, I tend to go with the old rules first rather than getting a fraction. For this next example, notice I do not have a fraction form. So I'm going to save any shifting until last. Getting a fraction makes it a little bit more complicated. So I can use my old rule of like bases multiplied. keep the base and add the exponents. And I have like signs, so I'm going to add and keep the sign. Then I'll deal with the negative exponent. So it's a negative exponent. I'm going to shift down and make the exponent positive. For this example, I can use my product to a power rule. So we're going to take this exponent and apply it to each piece of the product. So we have x to the fifth to the negative third, and we have y to the negative second to the negative third. And remember, power to a power, keep the base and multiply on the exponents. So I get x to the negative 15. And on the y, notice you have two negatives. That's going to give you y to the positive 6. And now I'll deal with any negative exponents. So only the x is no good. So right now they're both on the numerator. So the x is going to shift, go to the denominator. Its exponent becomes positive, and the y to the 6 stays on the numerator. Let's have a look at this problem, which has a fraction to a power. The first thing you should do is look inside and make sure that there's nothing in there that you can simplify. And there's not. So we're going to treat this problem as a fraction to a power. And the rule is take that outside exponent to the numerator and to the denominator. So we'll make two smaller problems. All right, there are two approaches from here. I'll work it separately with both. One thing that you could do, because both of these outside exponents are negative, you could shift the entire parentheses, and they're just going to trade places for this outside exponent. So we'll go that route for our first method. Everything inside stays the same. The outside exponent becomes positive, and this one that's down is going up. Outside exponent becomes positive. And now we'll work on each piece there. On our numerator, that is a product to the power. So we're going to have to take that outside exponent down to each piece. And I'm going to have to go down so I can keep it on my screen. So I'm going to have 2 squared x to the 7th squared. And I can keep working that. 2 squared gives me 4. And x to the 7th squared, power to a power, keep the base and multiply. So I get x to the 14th. Right, now go to the denominator. This outside exponent is going to each piece. So I have negative 3 squared. You want to use parentheses because you want the sign to go to the power. Originally it is inside, so it needs to stay inside. And you have y to the 4th squared. Negative 3 squared is negative 3 times negative 3 gives you a positive 9. And power to a power on the y, keep the base and multiply the exponents. For the other approach to this problem, we would first still treat it as a fraction to a power and change it into two problems, the numerator and denominator. So we'll take that exponent with our numerator and also with our denominator. The next step is the one that's different. Instead of shifting these right away, if you chose, you could clean each one up. And so the numerator is a product to a power. You could distribute that power down to each one. And so that would be a negative 3 to the negative 2 power. And it would be y to the 4th to the negative 2 power. We cannot work out the negative 3 to the negative 2 power. A number to a negative power you have to shift before you can work it out. So it's going to move down and get a positive exponent. This y we can work out, and that will be y to the negative 8 We'll leave it there for right now. Go to our denominator, and it is a product to a power, so we can take the outside exponent to each one. So we have 2 to the negative 2 and x to the 7th to the negative 2. The 2 to the negative 2 is a number to a negative power. We can't work it until we shift it. So we're going to shift it up, and it will get a positive 2 on the outside. And our x we can work out. Will give us x to the negative 14. And now we'll finish those up. So we have 2 squared gives us 4 on the numerator, and we'll just keep this one for a minute. On the denominator, negative 3 squared gives us a 9, and we still have the x. And then the x and the y are going to switch places because they both have a negative exponent. So my x is going up, gets a positive 14, and my y is going down. So it doesn't matter if you use this approach or if you use the first one, which actually moves the entire parentheses for that outside exponent. For this example, it is a fraction to a power. What you want to notice, though, is that you have some things inside that are alike. You should clean those up first before you deal with the outside exponent. So we'll work on the inside, and we're still going to be in the parentheses. So first of all, for our a's, we have a fraction form. Your rule is keep the base and subtract. So we have a to the 5 minus 7 gives us a to the negative 2, which is going to make it go to the denominator. And we won't write the one right away. We might get something else there and not need it. For the b's, your rule is subtract top to bottom, or you could shift this with the negative up. It's going to give you b to the 3rd. Either way that you go, 1 minus a negative 2, minus a negative makes plus, so it gives you b to the 3rd, positive exponent, so it goes on the numerator. And now we have a fraction to a power, so we'll break it apart into numerator and denominator, taking the outside exponent with each. So we have 2 little problems instead of one big one. We can go ahead and work these out, or you could shift the whole parentheses. It doesn't matter. If we work them out, power to a power, keep the base and multiply, gives me b to the negative 9. And on the denominator, a to the negative 6. And now they're both negative, so they're going to switch places. This one's going down, and this one is going up. So I'm going to have a to the positive 6 on the numerator and b to the positive 9 on the denominator. So if you see anything on the inside of a big parentheses that will clean up, you should work from the inside out and clean up first. And now our last example from the handout. We do have a fraction to a power. You will need to let this negative either go with the numerator or denominator because you're going to break it apart and make 2 problems. So I'm going to go ahead and take the negative with the numerator. So I have negative 1 to the negative 2, and I have 8 to the negative 2. Now, because the inside part here is a number to a negative power you cannot do. So these are actually going to have to shift before you can do any more work because the outside exponent is negative for both. It is not going to change anything on the inside. So we're going to have 8 to the positive 2. We still have negative 1, but now it's to the positive 2. We can work those out. 8 squared gives us 64. And negative 1 squared is negative 1 times negative 1 gives us a positive 1. And 64 divided by 1 gives us 64. Scientific notation. Scientific notation is used to write very large numbers or very small numbers without all the zeros. For example, in standard form, we have 523 million, or in scientific notation, we have 5.23 times 10 to the 8th power. The form of scientific notation is a number part times 10 to a power. The number is greater than or equal to 1 and less than 10. Or another way to say it is it always has one non-zero digit on the left of the decimal. To put numbers into scientific notation, step 1, find the appropriate place for the decimal. Step 2, use the X for times. Step 3, write 10 to a power. The power is the number of places you would have to move the decimal in the new number to get back to the original. If you would move to the right, it is a positive exponent. If you would move to the left, it is a negative exponent. Let's look at an example. Write 372 million in scientific notation. The first thing we have to do is choose the place for the decimal. The decimal has to go between the 3 and the 7. That will give us one non-zero digit on the left of the decimal, so a number that is between 1 and 10. That's the only place that the decimal can go. If it's after the 7, we would have 37. That's too big. If it's in front of the 3, that would be less than 1. That would be too small. So that's the only option for the decimal. So we have 3.72 our times 10, and then we'll choose our exponent. From here, our decimal, we have to go back to the original decimal. We'll count the spaces, and we would have to go to the right. So it's going to be positive, and it's going to go 8 spaces. Another way you can think of it is this is a very large number. You might think of a large number, a positive exponent, a large number. Let's look at another example. Write 0.0000712 in scientific notation. So this is a very tiny number. First step is to choose where the decimal should go. The decimal has to go between the 7 and the 1. That is the only choice. So we'll have 7.12 times 10, and then we'll choose our power. From our new decimal, to get back to the original, we would have to go to the left. So we're going to have a negative exponent, and we can count 1, 2, 3, 4, 5, 6. Or we can remember this is a tiny number, so it will have a negative exponent. Let's look at one more example where we can see the advantage of writing in scientific notation. The mass of a protein is approximately, and we see this extremely small number. Write this number in scientific notation. So our first job is to find the place for the decimal. It's going to go between the 1 and the 7. So we'll have 1.7 times 10, and very small number, we're going to go to the left to get back to the original, and we'll count 3, 6, 9, 12, 15, 18, 21, 24. So a negative 24. If you had to do some other operation with this number, like a scientist would have to, it would be much easier to operate with this number that's in the scientific notation than it would be with all the zeros. So this is the purpose of scientific notation. Standard or decimal form of a number. To convert numbers from scientific notation to decimal or standard form, you will perform the multiplication. Multiplying by a power of 10 moves the decimal to the right for a positive exponent and to the left for a negative exponent. We're going to convert to decimal form. This is also known as standard form. So we will just apply the multiplication. When we multiply and we have a negative exponent on our power of 10, it will move our decimal to the left 3 places. So we're going to move 1, 2, 3. So we're going to have to add some zeros to have enough spaces. So we moved 1, 2, 3 places, and make sure that you do write your decimal. Let's look at another example. Convert to decimal form, which is also known as standard form. 1.201 times 10 to the 8. This time we have a positive exponent, so we will move our decimal to the right 8 places. So if we start, we have 1, 2, 3 places. We're going to have to add 5 zeros to have enough. So 1, 2, 0, 1, and then we'll add 5 zeros. 1, 2, 3, 4, 5. So our decimal was between the 1 and 2. 1, 2, 3, 4, 5, 6, 7, 8. Now our decimal is at the end. We don't have to write a decimal after the number. We can put commas so that the number is easier to read. And so that number is actually 120,100,000.